Good afternoon to all of you. First of all, I want to introduce myself. Myself Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering. And today my content is GTU question paper solution of June 2009 of the subject of vector calculus and linear algebra. So let's see. Up to question number 4D, you already see. So here question number 4E. If u and v are orthogonal unit vectors, then what is the distance between u and v? Justify your answer. So for our convenience, we are taking two vectors of R3. Let u is equal to x1, x2, x3 and v is equal to y1, y2, y3. Now because of these two vectors are orthogonal, u and v are orthogonal, that means what? Inner product of u with v, that is equal to 0. So x1 y1, so inner product with Euclidean inner product of uv, how we define? Just simply dot product, that is x1 y1 plus x2 y2 plus x3 y3, right? And because of inner product uv equal to 0, we have x1 y1 plus x2 y2 plus x3 y3, that is equal to 0. Now distance of uv, how we define distance from any vector, one vector to another vector? We define with this manner, that is equal to under root x1 minus y1 square plus x2 minus y2 square plus x3 minus y3 square. Okay, because of u is equal to x1, x2, x3 and v is equal to y1, y2, y3. So that's why we define distance of uv, that is equal to under root x1 minus y1 square plus x2 minus y2 square plus x3 minus y3 square. Now simplify this equation, that is equal to under root x1 square plus x2 square plus x3 square plus y1 square plus y2 square plus y3 square, and next is we get minus 2 x1 y1 minus 2 x2 y2 and minus 2 x3 y3. So this three terms together we can write minus 2 into x1 y1 plus x2 y2 plus x3 y3, that is equal to under root x1 square plus x2 square plus x3 square plus y1 square plus y2 square plus y3 square. Because of x1 y1 plus x2 y2 plus x3 y3, that is equal to 0, we get x1 square plus x2 square plus x3 square plus y1 square plus y2 square plus y3 square, and this equal to under root summation xi square plus summation yi square. Now because of we know that that summation xi square, that is equal to x1 square plus x2 square plus x3 square, and that is exactly norm u square. Okay, because of we know that norm u is equal to inner product of u with u raised to 1 by 2. So norm u square, that is equal to inner product u with u, and when we take inner product u with the Euclidean inner product, we get x1 square, norm u square is equal to x1 square plus x2 square plus x3 square. So that's why instead of summation xi square we can write norm u square, and similarly instead of summation yi square we can write norm v square. Now because of u and v are unit vectors, that means what? Norm u, that is equal to 1, and norm v, that is also equal to 1. So use that property, we get under root norm u is already 1, so under root 1 square plus 1 square, that is equal to under root 1 plus 1, that is equal to under root 2. So here is the answer of this question, that if u and v are orthogonal unit vectors, then what is the distance between u and v? So the answer is distance between u and v, in that case that is equal to under root 2 when u and v are orthogonal unit vectors, right? So here the complete the solution of this question. Next question. Question 4F. Define algebraic multiplicity of an eigenvalue and determine the algebraic and geometric multiplicity of A, that is equal to, in matrix, 0 1 1 1 0 1. The first row is 0 1 1, the second row is 1 0 1, and the third row is 1 1 0. Here we have 3 cross 3 matrix. So the number of row and number of column both are 3. So this is a square matrix, right? If the eigenvalues of A are 2, -1, -1, and corresponding eigenvectors for lambda is equal to -2 is 1 1 1, and for lambda is equal to -1 are -1 1 0 and 1 1 -2. So first of all we have to define algebraic multiplicity of an eigenvalue. So here is the definition. First, the algebraic multiplicity of an eigenvalue lambda is its multiplicity as a roots of characteristic equation of determinant of A minus lambda I, that is equal to 0. So that means, what is the meaning of algebraic multiplicity? Suppose we have 3 eigenvectors, right? Lambda 1, lambda 2, lambda 3. Now as an eigenvalue, lambda 1 suppose occur in 2 times, so we can say that algebraic multiplicity of lambda 1 is 2, right? Suppose lambda 2, the second eigenvalue is lambda 2. Suppose as an eigenvalue lambda 2 is occur in only one time, then we can say that algebraic multiplicity of lambda 2 is 1, right? And then lambda 3, suppose in that lambda 3 as an eigenvalue occur in 3 times, so we can say that algebraic multiplicity of lambda 3, that is equal to 3. Okay. Now next question is, what is the meaning of geometric multiplicity? That also you have to understand that what is the meaning of geometric multiplicity. Geometric multiplicity is suppose we have eigenvalue lambda 1, right? Now corresponding to eigenvalue lambda 1, suppose we have 2 eigenvectors. Suppose we get 2 eigenvectors corresponding to lambda 1. So we can say that the geometric multiplicity of lambda 1 is 2, right? So that is depending upon the how many eigenvector corresponding to that eigenvalue. So that is depending upon that one, right? So suppose lambda 1, suppose we have eigenvalue lambda 1, right, and corresponding to lambda 1 we have 3 eigenvectors. So we can say that the geometric multiplicity of lambda 1, that is 3. Okay, right? So just try to understand that one. Here in this question paper only you need to write the definition of algebraic multiplicity. So here I just mentioned the definition of algebraic multiplicity. The algebraic multiplicity of an eigenvalue lambda is its multiplicity as a root of characteristic equation. So determinant of A minus lambda is equal to 0. Now you can see now next is all in this question. What next we have to find? Determine the algebraic and geometric multiplicity of A, right? If the eigenvalues of A eigenvalues are already given corresponding to all the eigenvalues, we have already eigenvectors in this question. So you have to just write down the algebraic and geometric multiplicity, right? Nothing else. So now next is, what is the question? Determine the algebraic and geometric multiplicity of A. Okay, so you can understand now from the question. See, we have 3 eigenvalues, 2, -1, -1, but 2 is occur in only one time and -1 occur in 2 times, right? So now as I told you, you can understand from this question that algebraic multiplicity of 2 is 1. Okay, algebraic multiplicity of 2 is 1 because as an eigenvalue 2 is occur in only one time. Now corresponding to 2, how many eigenvectors we have? Only 1, right? So the geometric multiplicity of 2 is also 1, correct? So algebraic and geometric multiplicity of 2 is 1, okay, because of as an eigenvalue 2 is occur in one time and corresponding to lambda is equal to 2, we get only one eigenvector. So that's why algebraic and geometric multiplicity of eigenvalue 2 is 1. Okay, now back to minus 1. Minus 1 as an eigen value, minus 1 occur in 2 times, so that's why algebraic multiplicity of minus 1 is 2, and as an eigen value minus 1 corresponding to lambda is equal to minus 1, we will get 2 eigen vectors, correct, we will get 2 eigen vectors. So that's why the geometric multiplicity of lambda is equal to minus 1, that is also 2. So algebraic and geometric multiplicity of lambda is equal to minus 1 is 2. Okay, so here is the answer. Now you can understand algebraic multiplicity of a is algebraic multiplicity of 2 is 1, and the algebraic geometric multiplicity of lambda is equal to minus 1 is 2. Okay, so next question. Next or question 4a, state Cauchy squares inequality and verify Cauchy squares inequality for the vectors u is equal to minus 3 1 0 and v is equal to 2 minus 1 3. Now statement of Cauchy squares inequality: if x and y vectors in Rn, then modulus of inner product of xy, that is always less or equal to norm x into norm y. So first of all we want to find inner product uv, so that is simply the dot product using Euclidean inner product. When we find inner product uv, that is equal to minus 3 1 0 into 2 minus 1 3, so that is equal to minus 6 minus 3 into 2 minus 6 plus 1 into minus 1, that is minus 1 plus 0 into 3, that is 0. So minus 6 minus 1 minus 7. So inner product uv, that is equal to minus 7. So modulus of inner product uv, that is equal to 7. Now also we want to find norm u. Now norm u is exactly inner product u with u raised to 1 by 2. So that means under root dot product of u with u, that is equal to u1 square plus u2 square plus u3 square. So we get 9 norm u, that is equal to under root minus 3 square, that is 9 plus 1 plus 0. So under root 9 plus 1 plus 0, that is equal to under root 10, and norm v, that is also under root v1 square plus v2 square plus v3 square, that is 4 plus 1 plus 9, that is equal to under root 14. Okay, so when we multiply this two term, norm u into norm v, norm u into norm v, that is equal to under root 10 into under root 14, that is equal to under root 140. So now you can understand that Cauchy squares inequality is easily satisfied here, particularly this example, because of inner product modulus of inner product uv, that is equal to 7, and norm u into norm v, that is equal to under root 140. So clearly 7 is less than under root 140, that's quite obvious. Okay, because this under root 140, that is approximately 11 point something, right, because 11 square is 121 and 12 square of 12, that is 144. So it's nearby 12 and approximately 11 point something, right. So clearly 7 is less than under root 140. So the Cauchy squares inequality is verified for the given vectors. Okay, so here the complete the solution of this question, question 4a. Next question, question 4b. Prove that inner product uv, that is equal to 1 by 4 norm u plus v square minus 1 by 4 norm u minus v square. Here is a solution. It's a one simple result that we have to prove. Solution: norm u plus v whole square, that is equal to inner product u plus v with u plus v that is equal to norm u square, right? When we distribute this step, this is in fact norm u with u, right? So this equal to norm u square plus 2 inner product uv plus norm v square, right? And similarly norm u minus v whole square, that is equal to norm u square minus 2 inner product uv plus norm v square. So subtracting 1 2 from 1, okay, so we are taking 1 minus 2, so that is equal to norm u plus v square minus norm u minus v square, that is equal to, when we take 1 minus 2, norm u square will be cancel out, right? Norm v square that is also cancel out. So we just get 2 inner product uv minus 2 inner product uv, so we get 4 inner product uv, right? So norm u plus v square minus norm u minus v square, that is equal to 4 inner product uv. So inner product uv is equal to norm u plus v square divided by 4 minus norm u minus v square divided by 4, okay, and that is our requirement, that is we actually need to prove, right? So here the proof of this simple one result. So the question 4b is complete. Next question 4c. Question 4c. Let T from R4 to R3 be the linear transformation given by the formulas T of x1, x2, x3, x4, that is equal to 4x1 plus x2 minus 2x3 minus 3x4, then 2x1 plus x2 plus x3 minus 4x4, and 6x1 minus 9x3 plus 9x4.